already seen how difficult it is to integrate powers of sine.
For example, what's the integral from 0 to pi over 2 of sine to the 32nd power? Well, it turns out that it's, what is this, 300,540,195 divided by 4,294,967,296 times pi. But how would I ever know this?
That looks so random. And yet, there's more going on here.
In fact, this ends up being 3 times 3 times 5 times 17 times 19 times 23 times 29 times 31 all over 2 to the 32nd power.
Oh, huh? All those numbers suggest something's going on here. That could hardly be an accident. The goal of computing, the goal of numbers, the goal of everything that we're doing in this course isn't just answers, it's insight. So how can we gain some insight into why that integral works out like that?
Specifically, a question is, why does it factor so nicely, right? I mean, there's no reason, at least at this point, for it to work out so nicely. So why does it factor so nicely?
Well, to gain some insight into this, let's use parts to examine the relationship between the integral of sine to the nth power and sine to the n-2nd power.
Well, let me write that down. To answer this question of why it factors, what I want to do is figure out some sort of relationship between the integral from 0 to pi over 2 of sine to the nth power and the integral from 0 to pi over 2 of sine to the n-2nd power.
We'll use parts.
So let's start with this, and I got to pick a u and a dv. So I'll have u be sine to the n-1, and dv, which will be the rest of this, will just be sine x dx. So u dv gives me this integrand. Now if that's u and that's dv, I got to figure out what du and v are supposed to be. Well, if dv is sine of x, then an antiderivative for that is minus cosine x. And if u is sine to the n-1, then du, it's got to differentiate this, that'll be the chain rule n-1 times sine to the n-2, and then times the derivative of this. What's the derivative of the inside? The derivative of sine is cosine, and then dx.
Now we get a formula from parts.
So this integral is uv, so sine to the n-1 times cosine with a minus sign, evaluated at pi over 2 and 0, minus the integral from 0 to pi over 2 of v du, which is, well, here's n-1 sine to the n-2 cosine squared dx, and I've got a minus sign there on the v, so I'll make that plus. Alright, now when I plug in pi over 2, that kills the cosine term, and when I plug in 0, that kills the sine term. So this thing here is just 0, and that means this original integral is just the integral from 0 to pi over 2 of n-1 times sine to the n-2x. And instead of cosine squared there, I'll write that as 1 minus sine squared x dx. Now I can expand this out. This is really the difference of two integrals after I expand. It's n-1 times the integral from 0 to pi over 2 of sine to the n-2x, but then minus n-1 times the integral from 0 to pi over 2 of sine to the n-2 times sine squared is just sine to the nth power dx.
And we can solve this.
So this is what I've got at this point. I've got that the integral from 0 to pi over 2 of sine to the n x dx is equal to this after I did parts. But now I can add n-1 times the integral from 0 to pi over 2 sine to the n x dx to both sides. And what do I get? Well, then I'll get n times the integral from 0 to pi over 2 sine to the n x dx is equal to, and on the other side, I'll have n-1, the integral from 0 to pi over 2 sine to the n-2 x dx. And then I can divide both sides by n. And if I divide both sides by n, right, I find that the integral from 0 to pi over 2 of sine to the nx dx is n minus 1 over n times the integral from 0 to pi over 2 of sine to the n minus 2 x dx. So this formula is telling me how to compute the integral of sine to the nth power in terms of the integral of sine to the n minus second power. So I get started by knowing that the integral from 0 to pi over 2 of sine to the 0th power of x dx, that's just the integral of 1 from 0 to pi over 2. Well, that's just pi over 2. So what's the integral of sine squared on the interval 0 to pi over 2? Well, using this formula, when n equals 2, I find that the integral from 0 to pi over 2 of sine squared x dx, this is when n equals 2, is 2 minus 1 over 2, that's n minus 1 over n, times the integral from 0 to pi over 2 of sine to the 0th power. But I know what sine to the 0th power is. That's just pi over 2. So this is 1/2, 2 minus 1 over 2, times this, which is pi over 2, which is pi over 4. So the integral from 0 to pi over 2 sine squared x is just pi over 4. What's the integral of sine to the 4th? Well, let's use this formula when n equals 4. So the integral from 0 to pi over 2 sine to the 4th x dx, well, that'll be 4 minus 1 over 4 times the integral from 0 to pi over 2 of sine squared x dx. And we just figured out what the integral of sine squared is, right? This is 3/4 times pi over 4. What's the integral of sine to the 6th? So that means I should look at this formula when n equals 6. So the integral from 0 to pi over 2 of sine to the 6th x dx is, well, if I put in n equals 6, I get 6 minus 1 over 6 times the integral from 0 to pi over 2 of sine to the 4th x dx. But I just figured that one out. So this is 5/6 times, well, here's the integral of sine to the 4th, times 3/4 times pi over 4. What's the integral of sine to the 8th? Well, that means I should use this formula when n equals 8. So the integral from 0 to pi over 2 of sine to the 8x dx is, according to this, when n equals 8, that's 8 minus 1 over 8 times the integral from 0 to pi over 2 of sine to the 6x dx. And we just figured out sine to the 6th. So this is 8 minus 1 over 8, that's 7 over 8 times the integral of sine to the 6th, which is 5/6 times 3/4 times pi over 4. Okay, we're seeing a pattern. What's the integral of sine to the 32nd power? So the integral from 0 to pi over 2 of sine to the 32nd power, just following this pattern, will be 31 over 32 times 29 over 30 times 27 over 28. And I'm going to keep on going until I get down to 5 over 6 times 3 over 4, and then finally times pi over 4. And now we can cancel like crazy. So this 3 and this 6 give me a 2. This 5 and this 10 give me a 2. The 7 and the 14 give me a 2. The 9 and the 18 gives me a 2. The 11 and the 22 gives me a 2. The 13 and the 26 gives me a 2. The 15 and the 30 gives me a 2. The 17 survives, right? Let's see what else I can cancel. The 19 is going to survive. The 21, however, well, the 21 is going to be killed by a 7 somewhere. I can find a 7 in this 28. So this gives me a 4, and this 21 gives me a 3 left over. Can I kill that 3 somehow? Yeah, that 3 can be killed by this 12 and give me a 4 left over. So this is entirely gone now. The 23 is going to survive. What about the 25? Do I have any 5s? Well, I've got a 5 in this 20. That gives me a 4. And then I've got a 5 here, which will end up surviving. I've got a 27 here. Do I have any 3s down here? Well, I've got a 3 in this 24. I can make this, this 24 into an 8 if I convert this 27 into a 9. The 29 is going to survive, and the 31 is going to survive. So in the numerator, what all do I have? Well, in the numerator, I've got a 31, a 29, a 9, a 5, a 23, a 19, and a 17, and way over here, a pi. And in the denominator, I've got a whole bunch of 2's, right? How many 2's do I have? Well, I've got 2 to what power? I've got 5 2's there, another 2 here, 2 more 2's, a 2, 3 more 2's, another 2, 2 more 2's, another 2, 4 more 2's, 1 more 2, 2 more 2's, 1 more 2, 3 more 2's, 1 more 2, and then here another 4 2's. And I just got to figure out what are all these numbers that I get when I add these things up. And 5 plus 1 plus 2 plus 1 plus 3 plus 1 plus 2 plus 1 plus 4 plus 1 plus 2 plus 1 plus 3 plus 1 plus 4. That's 32 2's in the denominator.
This was a triumph. I'm making a note here.
Huge success.